Put your hand on a table. Feels like the most ordinary contact imaginable. Your skin stops. The table pushes back. Case closed. But zoom down far enough, and the word touch starts to fall apart. There are no perfectly rigid surfaces down there. No tiny billiard balls making a clean little click. So what is stopping your hand from passing straight through? The short answer is electromagnetic interaction, quantum mechanics, and a nervous system that turns resistance into an experience. And yes, the claim that you never really touch anything is a trick, but it points towards something real. At our scale, touching is easy to define. Two objects are in contact when they interact strongly enough to exchange force. They can push, bend, grip, scrape, or vibrate against each other. That definition works whether or not their microscopic parts behave like hard shells. Even this table is not perfectly smooth. Under a microscope, its surface is a landscape of ridges and valleys. Your skin is another landscape. The highest points meet first, deform slightly, and spread the force through both materials. Zoom deeper beyond those surface details, and the classical picture stops being enough. Atoms contain positively charged nuclei and negatively charged electrons. But electrons are not little planets traveling on neat circular tracks. Quantum mechanics describes them with states and probability distributions, often drawn as fuzzy clouds. When the atoms in your hand approach the atoms in the table, those electron distributions begin to interact. Electric charge matters here. Rearranging the distributions costs energy, and the electromagnetic interaction creates the forces that push through the material. So the table does not need an invisible hard skin. The rising energy of forcing two pieces of matter closer together is enough to produce resistance. But electrons repel is still only part of the answer. Electrons belong to a family of particles called fermions. Fermions obey the Pauli exclusion principle. Identical fermions cannot occupy the same quantum state. That rule is not a force in the ordinary sense. Nothing is firing a tiny quantum spring between two electrons. Instead, it restricts which combined states are allowed. As two pieces of ordinary matter are compressed together, their electrons cannot all collapse into the same lowest energy arrangement. They must reorganize into different states, and many of those arrangements carry more energy. The result is a powerful resistance to compression. Electromagnetic interactions help bind atoms and molecules. The Pauli principle helps give electron matter its structure and volume. Together, with the detailed quantum behavior of bonds and materials, they help explain why the world around you is stable instead of collapsing into an ultradense heap. So if someone says solidity comes only from electric repulsion, that is incomplete. If they say it comes only from Pauli exclusion, that is incomplete too. Reality is a team effort. Now return to the hand and the table. To pass through, the atoms in your hand would have to move through an enormous organized structure of interacting electrons and nuclei. The permitted quantum states would have to be rearranged, chemical bonds distorted or broken, and vast numbers of particles displaced. At ordinary energies, that is overwhelmingly unfavorable. Instead, your skin flattens a little. The table bends by an amount too small to notice. Atomic bonds shift. A mechanical stress wave travels through the material. The table has not acted like an infinitely hard wall. Both objects have deformed and exchanged force. That exchange is what contact looks like in the real world. But physics has only explained why your hand stops. It has not yet explained why stopping feels like something. Pressure deforms your skin. Specialized sensory structures called mechanoreceptors respond to different kinds of deformation. Some are good at sustained pressure. Others respond rapidly to motion or vibration. They convert mechanical changes into electrical activity in sensory neurons. Those signals travel through nerves and the spinal cord toward the brain, where multiple streams of information help construct texture, pressure, shape, and motion. That smooth tabletop is not delivered to the mind as a tiny internal photograph. It is inferred from patterns of force changing across your skin as your fingers move. Touch is therefore both physical interaction and biological interpretation. This is where another famous phrase appears. Atoms are mostly empty space. It is useful, but dangerous if taken too literally. The nucleus is vastly smaller than the overall atom. That much is true. But the region around it is not simply a miniature vacuum with a few solid beads flying through it. Electron quantum states extend through that region, and electromagnetic fields are physically relevant there. Calling it empty can make you imagine that another atom should slide through if it aims carefully enough. But atoms do not behave like sparse solar systems made of classical objects. Their quantum states interact as wholes, and there is no universal microscopic gap that proves two objects are not touching. The apparent boundary depends on how we define and measure contact. At this scale, interaction is the more useful concept. So have you ever truly touched anything? If touch means two perfectly rigid classical surfaces occupying the exact same boundary, nature does not really offer those surfaces. If touch means two objects interacting strongly enough to exchange force, deform each other, and trigger sensation, then you touch the world constantly. The resistance is real. The table is solid. The sensation is real. What changes is the explanation. You are not feeling tiny hard shells collide. You are feeling the large-scale result of electric charge, quantum rules, material structure, and sensory signals, all compressed into one simple message from your brain. Stop. There is a table here. Which ordinary sensation should we zoom into next? Heat, color, or sound?